Welcome back to the third episode of the series. Glad to have you back. Today, I'm going to introduce the concept of action potentials, which are basically the bits of the neuroscience world. We will cover the stages of an action potential, as well as walk through the mechanisms that allow for action potentials to be carried in the right direction. By the end of the video, you should be able to answer the questions, what are the phases of an action potential? And how does the myelin sheath facilitate the efficient transmission of an action potential? The action potential is what is sent when a neuron fires, the electrical impulse that we defined our neurons by. The action potential provides a go button for synaptic activity. In the neuron, complex combinations of action potentials can signal for different responses to occur. There are four major phases of an action potential: rest, depolarization, repolarization, and return to rest. Let's take a look at these in turn and discuss what happens. The first or baseline case is when the neuron is at rest. Now, this doesn't mean that there isn't a membrane potential, just that there isn't a big change in current. The resting potential is approximately minus 70 millivolts, but even though we call the state rest, it's not like the neuron is completely inert. There are some leaky channels and other pumps keeping the neuron around this resting potential of minus 70. For an action potential to be triggered, the neuron's membrane needs to be brought up to a threshold of minus 55 millivolts. We'll see in a later video how this occurs. Once the neuron reaches threshold, voltage-gated sodium channels open, allowing positive sodium ions to rush in. Remember, the sodium-potassium pump established an environment with high sodium concentration outside and high potassium concentration inside. The opening of the sodium channels causes the membrane potential to rise rapidly as sodium rushes in. When the membrane potential becomes more positive, we say that the membrane was depolarized, explaining the name of the stage. The depolarization step is also called the rising phase, and the peak is called the overshoot. Soon after the rising phase, the previously open sodium channels close and are inactivated for about a millisecond. Meanwhile, voltage-gated potassium channels open up and allow potassium to leave the cell, dropping the membrane potential, so much that it even goes below the original resting amount. Thus, this phase is called the falling phase. After the undershoot, channels are closed and pumps work to reestablish our original gradient, completing the cycle of one action potential. You might be wondering how a neuron maintains such tight control over the timing of an action potential. Since it's the way neurons communicate, it's vitally important to make sure we can consistently and accurately send action potentials. Neurons make use of refractory periods to ensure that every step goes through. In fact, the reason pufferfish toxin is so dangerous is because it disrupts the neuron's ability to properly send action potentials. The 1 millisecond inactivation of voltage-gated sodium channels gives what's called an absolute refractory period. During this period, there is nothing we can do to open sodium channels, and therefore make another action potential, allowing our neuron time to reset. After absolute refractory period, there's also a relative refractory period, where it takes more work to get to threshold due to the undershoot from the opening of the voltage-gated potassium channels. It's not impossible to cause another action potential, but it does take more work than if the neuron was at rest. The combination of absolute and refractory periods allow for an action potential to propagate forward in the neuron. An action potential generally starts at the axon initial segment and then moves towards the terminal. Since the previous segment is in a refractory period while the next segment is at rest, the action potential will propagate towards the terminal instead of fizzling out or moving backwards. Alright, I'm introducing a new segment to the series where I periodically add review questions to help better drill the information in. Let's take a look at the inaugural question. A neuron is modified to have its voltage-gated potassium channels removed. Which of the following correctly describes a consequence of the modification? A. Nothing will change, the neuron will act as normal. B. The neuron will compensate by opening voltage-gated calcium channels to repolarize. C. The neuron will convert voltage-gated sodium channels into voltage-gated potassium channels. And D. The neuron will be unable to repolarize effectively. I'll give you a couple of seconds to pause and give your answer. The answer here is D. Without the voltage-gated potassium channels, the falling phase doesn't happen. The cell might eventually get back to rest, but it would take much longer than an unmodified neuron. We could have also used the process of elimination to solve this question. Answer choice A doesn't work because we're cutting out a major driver in our action potential. And B and C don't really make sense. Calcium and potassium have really different gradients, permeabilities, and E ion, and proteins don't magically convert like answer choice C said. So answer choice D is the only correct option. While some axons are unmyelinated, most have a sheath that helps conduct electricity better. However, the myelin sheath does not cleanly cover the entire axon. There are gaps where there isn't myelin called nodes of Ranvier or nodes of Ranvier. What this gives you is portions of the axon where the high amount of resistance from the lipid that is myelin blocks the conduction of electricity, as well as these nodes where big changes in potential can occur. The action potential jumps from node to node down the axon, and this process is called saltatory conduction. Okay, next review question. A neuron with no myelin sheath does not have which of the following features? A. Axon hillock, B. Nodes of Ranvier, C. Voltage-gated sodium channels, or D. DNA. I'll give you some time to think about it. Okay, the answer here is B. The nodes of Ranvier definitionally require a neuron to have a myelin sheath. The other choices are all things you would still see in an unmyelinated neuron. That wraps up my discussion for today. We talked all about action potentials, which show up all the time in neuroscience, so make sure you know what they are and how they work. As always, timestamps and extra info are in the description. I also wanted to say thank you to Dr. Reagan for her suggestion on the quiz questions. Thank you for watching, and I hope to see you next time.